So as we continue for the double integration method, we are now there is a procedure for the double integration method. So we have to assume that EI is constant in each segment of the beam. So the first one is sketch the elastic curve of the beam, taking into account the boundary conditions, zero displacement at pin and roller support, as well as zero displacement and zero slope at built-in cantilever support for example. So which means that the first procedure is you have to sketch the elastic curve of the beam that is due to the applied load on that particular beam. We have to set boundary condition. So if there is a pin or roller support, we have a zero displacement. If it is a cantilever support, it will have a zero displacement and a zero slope. The second one is use the method of section to determine the bending moment M at an arbitrary distance x from the origin. Always show M acting in the positive direction and the free body diagram. This assures that the equilibrium equations yield the correct sign for the bending moment. If the loading has discontinuous, a separate expression for M must be obtained for each segment between the discontinuities. So for this one, you have to use method of section so that you could determine the bending moment M at a certain distance x from the origin. So you have to always show that M is acting in the positive direction and the free body diagram. The third one is you have to, by integrating the expression for M twice, obtain the expression for EIV in each segment. Do not forget to include the constants of integration. So this means that you have to make use of the double integration formula. So you have to integrate twice our bending moment. And we have to, in our equation, as you have integrated the bending moment twice, do not forget to include our constant C sub 1 and C sub 2. Those are constant of integration. The last one is to evaluate the constants of integration from the boundary conditions and the continuity conditions and slope and deflection between segments. So after you have identified the expression for our M, or after we have integrated twice our M, and we have our C sub 1 and C sub 2, which are constant of integration, we have to evaluate the constant of integration, which means that we have to find the value for our C sub 1 and C sub 2 based on the boundary conditions and the continuity equation conditions on the slope and deflection between segments. So we have to take note that in double integration process, you have to consider each segment in the analysis of the deflection of beam using the double integration method. And frequently, only the magnitude of the deflection, called the displacement, is required. We denote the displacement small delta that is equivalent to the absolute value for our V. Okay, the first problem is a cantilever beam AB of length L shown in the figure carries a uniformly loaded distributed load of intensity W sub O, which includes the weight of the beam. So letter A, derive the equation of the elastic curve. Letter B, compute the maximum displacement of the beam, which is W 12 by 35 section using L equal to 8 feet. W sub O is 400 pounds per feet and E is 29 times 10 to the 6 psi. So to solve this problem, so we are going to section. So the first part is based on the procedure. We are going to section our beam, so by segment. So for this beam, we only have one segment, so that runs from point A towards point B. So that is segment AB. So for this one, we are going to identify the moment. So to solve for the moment, we are going to section the beam. So we're going to section here the beam. So if we try to section that one, so let us try to isolate. So we have here our beam. So we try to section considering the left portion of the beam. So this is point A. So of course, upon sectioning, so this will be our distance x, arbitrary distance x from point A towards the section side, and it will have our shear force V on the section side, and on the cut portion also on the section side you have your moment. So of course, for this uniform loaded, so we have here our load. So the resultant here, this is W sub O x, since the total length of our uniform loading now is x. So therefore, this distance is x all over 2. So from the centroid of this uniform loading towards the section side, this will be our reference point is x all over 2. So therefore, our moment here will be equivalent to, so this will rotate in a counterclockwise direction. So this will be negative W sub O times x multiplied to x all over 2. So this is the moment arm distance from the centroid towards the reference point, which is on the cut section. So therefore, this is negative W sub O x squared all over 2. So this is now our moment. So if we try to substitute the expression of our moment m to our differential equation, which is E I V's double prime is equal to m. So this will give negative W sub O x squared all over 2. So therefore, if we are going to integrate this one, so we're going to have first integration, so EI V prime, so we're going to have V prime is equal, first integration is equal to, use power formula. So our variable here is x. So from our power formula, if we try to recall, that will be u raised to n is equal to u raised to n plus 1 all over n plus 1. So our u here is our x. So simply our n is the exponent. We simply have to substitute to this equation. So we're going to have negative W sub O. This is of course a constant term, so you just copy that one. Then apply the power formula. So that will be x n plus 1. So that will be 3 all over, we have 2 here, all over n plus 1. So that will be times 3. So plus c of 1. So c is 2. This is the constant of integration. So we have integrated this on. So we have here negative W sub O x cubed all over 6 plus c sub 1. So that is the first integration. Now we have the second integration, EI. V is equal to power formula again. So negative W sub O x. So this is cube, so that will be 3 plus 1, so 4 all over 6 times n plus 1, so that will be 4 plus c sub 1 x plus c sub 2. So this is now on the second integration. So therefore this is equivalent to, so if we try to simplify, this will be equivalent to negative W sub O x to the fourth all over 24 plus c sub 1x plus c sub 2. Now we're going to identify the value for our constant of integration c sub 1 and c sub 2 based on our boundary conditions. So we have to take note that our beam is a cantilever beam. So meaning to say, as mentioned a while ago in our procedure for integration method, double integration method, that if that is a cantilever, there is no displacement. So we need to say zero displacement, and it will have zero slope. So let's start with the zero slope. So the first one is for the slope v prime equal to 0 when x is equal to L. So x equal to L, that is the total length of the beam from point A towards point B, from point B towards the support, which has a cantilever beam. So you need to say the support prevents rotation at point B. So if we try to substitute our V prime equal to 0 and x is equal to L into our equation from our equation, which is EI V prime is equal to negative W sub O x squared x cubed all over 6 plus C sub 1. So V prime is 0 is equal to negative W sub O L cubed all over 6 plus C sub 1. So therefore, our C sub 1 is equal to negative W sub O. This is equivalent to positive W sub O L cubed all over 6. So we have now the value for our C sub 1. Now for our C sub 2, we have to take note that there is no deflection for a cantilever beam. So point B, which is on the cantilever side, prevents deflection. So therefore, B is equal to 0 when x is equal to L. That is the total length of the beam. So this meaning to say the support prevents deflection at point B. So with our V is equal to 0 and our x is equal to L. So therefore, from our equation, EIV is equal to negative W sub O x to the fourth all over 24 plus C sub 1x plus C sub 2. So we can have our equation, we simply have to substitute our V, which represents for deflection, equal to 0, which is equal now to negative W sub O L to the fourth all over 24 plus, so plus C sub 1 is substitute WL cubed all over 6 times L plus C sub 2. So we got here W sub O to the fourth all over 24 and W of L cubed times L all over 6. So we simply have to get the least common denominator. The least common denominator here is 24. So if we have here 24, so that will be, so this will be 0 is equal to 24. So this is negative W sub O L to the fourth, then plus 24 divided by 6 is 4. So times 1. So this is 4 W sub O L to the fourth. So we try to simplify this one. So we get here a value of, here we have a value for 0 is equal to 3 WL to the fourth all over 24, or simply this is plus C sub 2. So we have here plus C sub 2. So if we try to simplify further, we got now the value for C sub 2. Our C sub 2 here is, C sub 2 is equal to negative 3 W L to W sub O L to the fourth all over 24, or simplify, this is negative W sub O L to the fourth all over 8. So this is now the value for our C sub 2. So this is our elastic curve equation. We substitute this value for C sub 1 and C sub 2. So this becomes now negative W sub O x to the fourth all over 24 plus W sub O L cubed all over 6 x minus W sub O L to the fourth all over 8.